Look, here is the reality of the situation. Mastering this specific grounding phenomenon, it isn't just some academic exercise. It is literally the exact difference between a highly functional product and a failed prototype that just ends up in the trash bin. As Henry Ott points out in his really definitive work on electromagnetic compatibility engineering, the way we connect our circuits to a shared ground can fundamentally sabotage the entire system. To truly grasp how perfectly good, perfectly designed circuits fail when sharing a ground, we have to stop looking at the schematic as this perfectly ideal diagram.
To understand how this failure happens, we need to look past the surface and dive straight inside the material itself. Imagine we're zooming right in, down into the microscopic structure of a standard copper ground trace on your PCB. On a schematic, a line connecting two ground points implies an instant, totally frictionless path, right? But down here at the material level, that copper trace is actually a physical highway packed with obstacles.
And the defining rule of our physical highway is ground impedance. As Ott states, absolutely all conductors, and that includes ground conductors, have finite impedance. Now, this impedance consists of two main things. You have your inherent resistance to DC current and your inductance to AC current. Because of this finite impedance, any ground conductor that is longer than 1/20th of a wavelength is just not a low impedance path anymore. It becomes a physical barrier.
This brings us to a visual analogy I want you to never, ever forget. Let's compare an ideal ground to a real ground using a water pipe. In an ideal circuit diagram, the ground is like an infinite, empty ocean where you can just dump current without ever raising the water level. It's 0 volts everywhere, always. But a real ground trace? It's more like a long, shared, friction-filled water pipe. As more circuits dump their current, their water, into this shared pipe, the friction, or the resistance, causes the water pressure to build up. In electrical terms, that pressure drop is a voltage rise. And because of this, two physically separated points on a ground conductor will literally never be at the exact same potential.
So this brings us directly to the mathematical reality laid out as our golden rule. Let's break this down methodically. We have V sub G, which equals I sub G multiplied by Z sub G. V sub G is the ground noise voltage. That's the voltage rise, the actual interference we are desperately trying to eliminate. I sub G is the ground current flowing through the trace, and Z sub G is the ground impedance of that specific trace. This really simple equation physically tells us that to minimize ground noise, you only have two choices, really. You must either minimize the ground impedance, Z sub G, or you must decrease the current, I sub G, by forcing it to flow through a completely different path.
Okay, so let's see what happens when we ignore this rule. Consider the common daisy chain single-point ground system. If you look at how Circuit 1, Circuit 2, and Circuit 3 are wired, they are in series. This is often called a common ground because they all just share the same return path to the main earth ground on the left. Now, because of its wiring simplicity, it's incredibly common. But, as the source explicitly notes, from a noise standpoint, it is the absolute most undesirable single-point setup you could possibly build.
Let's apply our golden rule to this daisy chain and see exactly why it fails so hard. When we calculate the voltage at point A, which happens to be the ground connection for Circuit 1, the equation reads like this. V sub A equals the sum of I sub 1 plus I sub 2 plus I sub 3, and all of that is multiplied by Z sub 1. Now, why is the math structured exactly this way? It's because the current from all three circuits has to travel back through that very first impedance segment, Z sub 1, just to get home to the ground point. So the crucial takeaway here is that point A is absolutely not at 0 volts. It's being lifted above 0 by the combined current of every single downstream circuit.
And you know, this compounding effect gets even worse when we calculate the voltage at point C, which is the ground for Circuit 3. V sub C equals the sum of all three currents multiplied by Z sub 1, plus the sum of I sub 2 and I sub 3 multiplied by Z sub 2, plus I sub 3 times Z sub 3. Notice that compounding effect. The ground potential at Circuit 3 is the sum of the voltage drops across every single trace segment in the chain. And if you look closely, Circuit 1's ground potential at point A is directly carrying the current of Circuit 3. If Circuit 3 is, say, a noisy high-power device, it's going to violently swing the ground voltage of Circuit 1 up and down through that shared Z sub 1 impedance.
Let's actually nail this down with a rigorous, real-world example using strict mathematical values. We want to see this disaster unfold. So we have our daisy chain. Circuit 1 is a sensitive analog sensor, drawing 10 milliamps. Circuit 2 is digital logic, drawing 50 milliamps. And Circuit 3 is a high-power motor driver drawing a massive 2 amps. Let's assign a highly realistic trace impedance of 50 milliohms to each segment, so that's Z sub 1, Z sub 2, and Z sub 3. Our goal here is to calculate the exact ground noise injected into circuit 3 when that big motor driver kicks on.
Step by step, let's plug these numbers right in. Step 1. We substitute our currents. I sub 1 is 0.01 amps, I sub 2 is 0.05 amps, and I sub 3 is 2.0 amps. Our Z values are 0.05 ohms across the board. Step 2. As we simplify the terms for the Z sub 1 drop, we sum all those currents. 0.01 plus 0.05 plus 2.0 gives us a total of 2.06 amps. We multiply that by 0.05 ohms. Step 3. We add the Z sub 2 drop, which is 2.05 amps times 0.05 ohms. And finally, the Z sub 3 drop, which is just 2.0 amps times 0.05 ohms. I want you to notice how that massive 2-amp current completely dominates every single part of this equation.
And boom, here is the dramatic result. When we add up those voltage drops, 103 millivolts plus 102.5 millivolts plus 100 millivolts, we get 305.5, or roughly 306 millivolts. Because of that shared daisy chain, you have literally just injected 306 millivolts of noise straight into the ground reference of your circuits. For a sensitive low-voltage analog component, a 300 millivolt swing on its ground pin is an absolute fatal blow. It's game over. This perfectly illustrates why the text clearly mandates that you should never, ever use this configuration between circuits operating at widely different current levels.
Now, you might be sitting there thinking, okay, well, I'll just use a separate parallel ground for every single circuit and problem solved. But actually, hold on, because here is the major gotcha from the text that trips up even the most seasoned engineers out there. Single-point grounds, even perfectly parallel ones, they're generally only effective at low frequencies. We're talking from DC up to maybe 20 kilohertz, but they generally fail completely once you get above 100 kilohertz. Let's see exactly why that is.
At high frequencies, a totally new phenomenon takes over. You have to account for parasitic stray capacitances. These are invisible, unintended capacitors that spontaneously close the gap between your separate ground wires. This stray capacitance takes your carefully, beautifully designed single-point ground and unpredictably turns it into a high-impedance, messy multi-point ground loop. The long lead lengths start acting as inductors, and at odd multiples of a quarter wavelength, those separate ground wires literally stop being grounds entirely, and they become highly efficient radiating antennas.
All right, let's rapidly lock in the 3 most critical engineering takeaways from everything we've derived today. First up, ground is never truly 0 volts. Because every conductor has impedance, the golden rule V equals I times Z absolutely guarantees a voltage drop. Second, avoid daisy chains for mixed signals at all costs. As our math proved, they allow high-power motor drivers to completely ruin the ground reference of your sensitive sensors. And third, watch your frequencies. Stray capacitance limits the effectiveness of single-point grounds to under 100 kilohertz. Above that, you really must transition to a multi-point ground plane system.
So the next time you go to drop a via to a ground trace, I really want you to ask yourself, is your PCB's ground acting as a solid reference, or is it actually a friction-filled pipe, or worse, a radiating antenna in disguise? Understanding these fundamental physical and mathematical rules is exactly how you guarantee your design actually survives the real world. If you found this breakdown valuable, make sure to hit subscribe for more EMC and automotive communication protocol survival guides. Keep your impedance low, and I'll see you in the next explainer.